Hey everybody, here we are. I'm calling it 10.2 even though it's not really the 10.2 in the book. We're now working with the calculus on parametric polar and vectors. We're going to start today with derivatives, and then the next video we do will be on integrals. So we're starting with parametric, and so let's just jump in with some examples. We're given a function here, x of t equals 2t minus 3t, and y of t equals 5 cosine t, right? So again, parametric functions are just the x piece is defined as a function of t, and the y piece is defined as a function of t. We're being asked to find dy dx. So what we're going to end up doing is we're going to find dx dt, right, the derivative of x respect to t, which in this case is 2t minus 3. And we're going to go ahead and also find dy dt, which is the derivative of 5 cosine t, which is negative 5 sine t. And then if we want dy dx, well, if I divide dy dt by dx dt by dx dt, then you can see how this is going to work out to be like if you multiply by the reciprocal, this is going to be dy dt equals, not equals, times dt over dx, right, multiplying by the reciprocal, and the dt's will cancel and you'll be left with dy dx, which is what we want. Right, so basically what that means is I need to take the dy dt and divide it by the dy dx, right? So if I want dy, the derivative of y with respect to x, then I need to take dy dt and divide by dy dx, right? So here we're going to have negative 5 sine t, and on the bottom we're going to have 2t minus 3. And that would be it. Like that is the derivative with respect to x, right? So we're done on that. Next one, it looks like it got cut off a little bit. It should say x of t equals 5t minus 2. So yeah, it should be 5t minus 2, so just like that. So that's the x piece, and then the y piece is 9 minus t squared. And then there's also this piece that got cut off. Our interval should be from negative 5 to 5. We want to find the equation of a horizontal tangent line to the curve. So you can imagine, I'm going to write this up here, you have some curve, and you have a horizontal tangent line, right? What's true about horizontal tangent lines? Well, we know that the slope equals 0. Another way of thinking about slope is dy dx equals 0. And a fraction is equal to 0 when its numerator is equal to 0. So we need to set the numerator, the dy piece, equal to 0. So I don't even really need to take the derivative of x yet. I just need to find dy dt, which is the derivative of this, which is negative 2t. Set it equal to 0, because I want to know when is it 0. And it turns out it's 0 when t equals 0. Now, I want to find the equation of any horizontal tangent line. So we could start with y. This is the equation of any tangent line. The fact that it's horizontal should tell you something already. What does the fact that it's horizontal tell you? Remember we said the slope of horizontal lines is 0, so that slope should be 0, which means like none of this even matters, right? This is all going to go away. And what we end up needing is this y coordinate, right? Horizontal lines are equations like y equals 7 or y equals 10. So how do I find this y coordinate? Well, we know that the horizontal line occurs when t equals 0. So I just need to take this t equals 0 and plug it in to the y piece, and I'll have a y coordinate, right? So we can go up to our y piece and we can say what's y of 0 is going to be 9 minus 0 squared, which is 9. So this y coordinate is 9. And you can go ahead and solve and just say, well, y, the equation itself is going to be y equals 9. That's the equation of that horizontal tangent line. All right, let's look at example 3. Let's make sure everything's here. The equation of a horizontal, the function defined 5t squared minus 5t. And there's a plus 2 down here. And then y of t is this. We want to find the equation of the tangent line. So again, since we're trying to find a tangent line, we're going to write this, and then we're trying to find all these different pieces when t equals 1. So let's just start. I don't know, there's many places you can start, but basically the idea is we need a coordinate point, and this is going to occur when t equals 1. So we can just find x of 1, right? If x of 1 is going to be 1 minus 5 plus 2, which is negative 3, and then y of 1 is going to be 1 over 1 plus 2 squared, which is 9. This is negative 2. And so we could rewrite this equation now as y minus 9 equals, we still don't know what m is, x plus 2. And now we need to find the m, which the m is dy dx, right? This change in y, change in x. So in order to do this, we need to find dy dt and dx dt and divide by them, right? So I'm going to go ahead and write it out. Dy dx is going to be the derivative of y, which is, we have to take the derivative of this thing, which I personally find it easier to take the derivative of that if we write it as this first. You could use quotient rule, but then you have to simplify a little bit. And then the derivative is going to be negative 2t plus 2 to the negative 3. So that piece is, let's do a different color here. Negative 2 over t plus 2 to the negative 3. And it's all going to be divided by dx dt, which dx dt is the derivative of the x piece up here, right, which is 2t minus 5. We want to know the slope. We want to know the slope when t equals 1. So we're plugging in 1. It's going to be negative 2 over, no, sorry guys, this should be positive 3. Once you move it to the bottom, it becomes positive 3, the exponent. We're plugging in 1. It's going to be 3 to the third, which is 27. Divided by, plug in 1 on the bottom, you're going to get negative 3, which is kind of like negative 3 over 1. So you can multiply by that, which is going to give us negative 2 over negative 81, which is just 2 over 81, and that's our slope. So we could take this number, plug it back in up here to get y minus 9 equals 2 over 81 x plus 2, and that's the equation of our tangent line to that function. Alright, so before we actually go over the speed and acceleration of parametrically defined functions, I just want you to think about what's actually happening here. So I guess I can do this right here because we got a little bit of extra space. So imagine when you're plotting a parametric function, you're plotting you're basically plotting x and y points, but they have like a t value as well. So like you'd plot, x, y, and then you'd have some other, like later on in time, you'd have another, you know, x2, y2, and it used to be x1, y1. And when you do this, you can always like write out, you can always find that there's a triangle in here, right? And remember, like, this particle's moving with, like, so like imagine this particle would have moved there after a certain amount of time, right? And so like in these questions we're going to be asked to find the speed or something like that, right? And so like if you, so let's think about what's in this triangle. What is this distance here? Well, it's basically x2 minus x1, right? It's the distance between them. It's also the change in x, right? That's how much x has changed. And then this piece right here is y2 minus y1, which is the change in y. And so if we wanted to find this, which is going to tell us the change in actual position, which is known as, change in position is like velocity or speed, right? And then to find, use a different color, to find this blue piece here, it's the change in actual position. Change in position is known as speed, right? That would just be, you'd have to use Pythagorean theorem and do like, you know, delta x squared plus delta y squared, and that will give me the, basically the velocity squared, the change in position squared over time. And then you could take a square root of both sides, and basically what you're getting is this formula where the delta x is dx dt is the derivative, and delta y is the derivative of y. Right? So I don't want you to just think like, oh, there's a formula there, but like there's a, like it just comes from like some basic Pythagorean theorem stuff. So let's go ahead and do this. We want to find the speed of a particle whose motion is defined by x coordinate, y coordinate. So the first thing we're going to do is just go find dx dt, which is in this case just 3, and we'll find dy dt, which is 9 minus 6t. And then if we want to, so like again visually what this is saying is if you have a triangle, the change in x is defined by the 3 and the change in y is defined by 9 minus 6t. We want to find the velocity, basically, you know, it would be velocity if it had a direction, but we're not going to give it a direction. We're going to end up only taking the positive case, which is speed. And because we're given that we want to know it at t equals 2, basically this just turns into 9 minus 12, which is negative 3, right? So we have like that distance, negative 3, this one's positive 3. So if we want to know the speed, it's going to be the square root of 3 squared, which is just this guy squared, plus negative 3 squared, right, which is just this guy evaluated at 2. Right, and then we can go ahead and simplify this. We're going to get square root of 9 plus 9, which is square root of 18, which if you wanted to, you could say, well, 18 is, you know, 18 is the same as square root of 9 times the square root of 2, so this would be 3 square roots of 2. That's the speed. Right, speed. Again, velocity would have to have like a sign, because we took squared something and then took the square root, it's always going to be positive. This gives us a speed. Acceleration is, if you notice up here, is basically just the second derivative. We just want to know, like, in the x direction, how fast is the x, what's the rate of change of the x coordinate, and what's the rate of change of the y coordinate. So we already have the first derivative, the second derivative, right? d squared x dt squared is going to be the derivative of 3, which is 0. And d squared y dy dt squared is going to be the derivative of 9 minus 6t, which is just negative 6. And so our acceleration is just going to be, this is like vector notation, 0, negative 6, which means in the x direction it's not accelerating at all. In the y direction it's accelerating negative 6 units per time unit squared. Right? Let's do another example real quick. This one only wants find the speed of the particle when t equals 1. So again, we're going to start with oh no, so there's look at this, right? Notice how it's not defined parametrically right now, right? The y coordinate is defined in terms of x, and the x coordinate is defined in terms of t. I think that's not supposed to be there. And so we can't apply any like this parametric reasoning if it's not in parametric form. So why don't we go and convert it to parametric form? We know that x is 1/2 t squared, so I can replace this x with what x is. So we're going to write y equals 1/2, and we're going to put in what x is, which is 1/2 t squared. And we're going to simplify this, and we're going to get 1/2 times, this is going to be 1/4 t to the 4th minus 1/4, and then clean it up a little bit more. We're going to get t to the 4th over 8 minus 1/4, and our x piece is, all right, so this is how the y coordinate is defined. The x coordinate is defined by this. Now we want to know the speed of the particle when t equals 1. So we're going to plug in 1 in both equations, right? Y equals, it's going to be 1 to the 4th over 8 minus 1/4. And the x piece is going to be 1/2. Let's clean this up. Is 1/8 minus 1/4. 1/4 is 2/8, so this is going to give us negative 1/8. Oh, you know what? I just realized there is I didn't even see this. There's like an ln(x) right here that's kind of floating around that is supposed to be in here. So this y piece should also not just be negative 1/4, but it should be negative 1/4 ln of, we had to plug in x there, right? So ln of 1/2 t squared, right? So this is ln 1/2 t squared. Which means, oh geez, and I never even took the derivative, so please ignore what I've been doing. This has been wrong. I haven't even taken the derivative yet, right? I don't want to just know x of t and y of t. I want to know the actual derivative at those points. So let's go back to this. And we need to take the derivative of this to find dy dt, right? Because that's what we're interested in. So this is going to become 4/8, which is 1/2 t to the 3rd, minus the derivative of natural log is u prime over u. So that's going to be the derivative of 1/2 t squared is t divided by 1/2 t squared, which we can clean this up, and it's going to be like this. And dx dt is just the derivative of 1/2 t squared, which is just t, right? So now let's see. And I messed this up again. This should not be there because with this t, This t is canceling with that, and there's just a t down there, right? So now we're ready to plug in our t value to find the dy dt, the numerical value of it, which t is 1. So if I plug in 1, we're going to get 1/2 minus 1/2, which is 0. So all that work just to get 0. Isn't that nice? And dx dt is 1. You plug in 1, you get 1. And so the speed is going to equal the square root of 0 squared plus 1 squared, which turns out to be 1. The speed is 1. All right, that's that. Let's keep going. All right, derivatives of polar equations. Before we start doing this example, maybe let's use this space over here to do some stuff, right? So notice, so we're going to use this to do stuff. Notice how for polar equations, if I had typed this correctly, so let's fix this first. This should be y equals r sine theta, and then the x piece is r cosine theta. I think I messed it up on the last one too. The y is always with sine and x is always with cosine. But what I'm trying to get you to notice is these polar equations, if you define them like this, they're kind of like parametric in that the x piece is being defined separately and the y piece is being defined separately. Except instead of being functions of time, they're functions of theta. And so if I wanted dy dx, basically that would just be dy d theta over dx d theta. All right, just like we did with parametric functions. So what I want to do first is just create the general case where let's find dy dx. So let's start by finding dy d theta, right? We're taking the derivative of this. Notice that it's going to require product rule because we have r times sine theta. So we're going to take the derivative of r with respect to theta. And then, so that's u prime, and then v is going to be sine theta. And then we're going to add that to the derivative of sine, which is negative, just cosine, times r, which we can put this, let's put that r in the front because otherwise we get confused of whether it's multiplying the theta or the cosine. All right, so that's dy d theta, and we can find dx d theta, which is the same idea. We're taking the derivative of that x piece, so that's also going to be dr d theta times cosine theta plus r, and then the derivative of cosine is negative sine, so it's actually going to be negative sine theta. So let's go ahead and just change this to a minus sign. Right, and then if I want dy dx, it's just going to be the y piece divided by the x piece right? And then you don't want to memorize this formula. You just kind of want to figure out well, how do we get there? What's the idea to get here? Because it's very similar to parametric, right? And so the idea would be if I wanted to find dy dx, I would need to know the value of theta at which we need to evaluate this, and I would also need to know dr d theta, and then we would be able to do this. So let's look at an example. We're going to find the equation of a tangent line to this curve, this parametric curve, when theta equals pi over 4. Right, so the equation of a tangent line is y minus y1 equals mx minus x1, where m, again, is, because we're using y as an axis, m is dy dx, right? So we need to find dy dx. We also need to find the x and the y, which we can do that pretty easily. Let's find the y coordinate. We just take our function here, and we take our r. To find r, we have to know what r is, right? So let's find what r is first. If I plug in pi over 4, sine of pi over 4 is root 2 over 2. So this is going to be 2 plus 2 times root 2 over 2 is just 2 plus root 2. Come on, don't do this. Right, 2 plus root 2. So that's my r. So in my y coordinate would be 2 plus square root of 2 times sine of theta, which again, sine of pi over 4 is root 2 over 2. Right, so that's my y coordinate. We can find the x coordinate similarly by plugging in. R is going to be the same, so it's going to be 2 plus square root of 2 times, x is not r sine theta, x is r cosine theta, and then so this is r times cosine of theta. Cosine is also root 2 over 2 at pi over 4. And so these are what would go up here for those. We also need to find the slope, which is the challenging part. So we need dy dx, which we could recreate this, or we can just use this now, right? So dy dx, the slope, m equals dy dx, is going to be given by this whole thing, but dr d theta is something that we can now find, right? Because we have a function of r and theta, we can find dr d theta. So let's just quickly find dr d theta, put it somewhere that's not in our way. Let's do it up here. Dr d theta is going to be the derivative of 2 is 0. The derivative of 2 sine theta is going to be 2 cosine theta. So dr d theta is 2 cosine theta. So here, when we're writing out this thing, it's going to be 2 cosine theta times sine theta minus r cosine theta all over, again, 2 cosine theta, that's that dr d theta, times cosine theta minus, I'm not sure why I have a minus on one of these. Look, there was a, let's go way back here. There's a plus sign here. That should be plus. So don't mess up that. Minus r sine theta. And then it's just a matter of figuring out, like, we know what theta is, and we actually already figured out what r is too, right? So we can plug all that stuff in. So this is going to be dy dx equals 2 cosine theta is pi over 4 times sine pi over 4 plus the radius, which was 2 plus square root of 2 cosine of pi over 4. Right, this 2 plus root 2 just came from what we found previously up here. Right, and then this whole thing is divided by the bottom, which is dr d theta again, which is 2 cosine theta, 2 cosine of pi over 4 times cosine of pi over 4. We could just do cosine squared. And this is the one that is minus r, which is 2 plus root 2 sine of pi over 4. And then we have to evaluate this whole mess, right? We actually need to figure out what number is this, which is pretty disgusting, but doable. So here we go. Both cosine of pi over 4 and sine of pi over 4 are root 2 over 2. So this is basically going to be 2 times root 2 over 2 times root 2 over 2. That's that cosine and that sine. Plus 2 plus root 2 times root 2 over 2. That's cosine of pi over 4. Same thing on the bottom. It's going to be 2 cosine of pi over 4 times cosine of pi over 4 is like cosine squared, right? So that's like root 2 over 2 squared minus 2 plus root 2 times root 2 over 2. And we keep going with cleaning this up. Simplifying this is going to give us root 2 times root 2 is 2 over 4 times 2. 2 over 4 times 2 is 1. So that's 1. Plus, distributing that root 2 into those parentheses here, we're going to get root 2, right? 2 times root 2 over 2 is root 2, plus 1. And then on the bottom, it's going to be pretty similar. The only difference here is the minus sign, right? Unless I mess something up. This is going to give us 2. No. So we're doing this. This squared is the same thing, right? It's 2 over 4 times 2, which is 1. So that gives us 1. Then minus. If you distribute this in there, we get the same thing as we did before. It's going to be root 2 plus 1. It's going to be root 2 plus 1. And this whole thing could simplify a little bit more into 2 plus square root of 2 over negative root 2, right? These 1s are going to cancel. You just be left with negative root 2. And I don't know, if we really wanted to, we could like rationalize this thing. But I think it's okay the way it is. So let's leave it like it is and let's just finish writing our equation, right? So our whole goal is to write the equation with tangent line. It's going to be y minus our y coordinate, which was this thing. If we actually like multiplied that in there, which maybe we should have done earlier just to save ourselves some trouble, we'd get 2 root 2 over 2, so it's going to be root 2 plus 1, which equals our slope, which was 2 plus root 2 over negative root 2 times x minus our x coordinate, which is also going to be root 2 plus 1. And that would be the equation of our line. So yeah, it's a lot of work. A lot of places to make mistakes, right? You gotta know your unit circle. Luckily there was not very many trig identities in there. Let's finish this and do our last little piece, which is velocity and acceleration of vector valued functions. So you know, vectors can be given as, you know, like an x piece and a y piece Sometimes they're also given as like, you know, like the x piece I plus the y piece j, like they assign these things to them, which as long as you understand that it means the same thing, you don't really need to know why. The speed, we've already kind of talked about this. It's the same as like a parametric function, and the acceleration is also the same as a parametric function. It's like velocity, like vectors are basically parametric functions. Like they're pretty much the same thing. Just you can do more with vectors. So let's look at this. The position function r equals t to the third t squared. What this is basically saying is that you could think about this as a parametric function, right? The x piece is being defined by that, the y piece is being defined by that. Then that describes the path of an object moving in the plane. We want to find the velocity acceleration of the object at 8,4. So the velocity is just going to be, you know, what it says, dx dt dy dt. So again, this first piece is the x piece, and this second piece is the y piece. So the velocity is just going to be 3t squared and then 2t. The trick here is we want to find it at the point 8,4, right? So we need to like somehow use those to find the exact velocity. And I guess the trick here is like they're giving us the x and the y, but really what we need to plug in here are t values. And so you have to imagine, like, in order to get 8,4 out of this, right? We wanted to get 8,4 out of this. You know, what number do I have to plug in for t? So when I do t cubed, I get 8. And when I do t squared, I get 4, right? What number cubed gives me 8? Squared gives me 4. Well, that's t equals 2. So this point 8,4 occurs when t equals 2. And so the velocity is just going to be at, you know, the velocity at time 2 is just going to be 3 times 4, which is 12, 2 times 2, which is 4, right? That's the velocity. Then it also wants the acceleration. The acceleration is the next derivative, right? You can just, again, it's just the derivative of this piece, 6t, and the derivative of that piece, 2. And again, it's going to be at t equals 2. It's just going to be plug in 2, and you're going to get 12, 2. All right, maybe we come back and do example 2 in a second, and I'll write it up there for you. Let's do example 3. It wants the velocity, acceleration, tangent, and normal vectors for an object on a path defined by the vector valued function. So our function we're given is r of t equals e to the t cosine t, like that, like this. So our function, let's just write it out, is e to the t cosine t e to the t sine t. And again, like, all they're doing here is they're defining, like, you know, this is how the x coordinate changes. This is how the y coordinate changes. So it's almost exactly like parametric, except, you know, just the way it's written is a little bit different. So start with velocity. It's nice they give us t equals 2 here. So the velocity is just going to be the derivative of the x piece and the derivative of the y piece separately. Right, and so it's just going to be, you have to take the derivative of e to the t cosine t, which is going to require product rule. And then we have to plug in pi over 2. But let's just do this. Maybe we'll just use the space for sample 2 to do this. So let's do this. dx dt, the derivative of the x component is going to be e to the t cosine t plus derivative of cosine t is actually negative e to the t sine t, right? And then evaluated at pi over 2. Cosine of pi over 2 is 0, so this piece just becomes 0. And then so it's going to be negative e to the pi over 2. Sine of pi over 2 is 1, so this is just negative e to the pi over 2. Same idea for the y piece, right? dy dt, the derivative of the y coordinate there is going to be e to the t sine t plus e to the t cosine t, and evaluated at 1 is going to be, sorry, not at 1, at pi over 2 is going to be e to the pi over 2 times 1, and then this piece is 0 because cosine of pi over 2 is 0, so we just get e to the pi over 2. All right, and the next thing it wants is the acceleration, which means we have to take the second derivative. So let's see. Okay, so we have to take the derivative of, we have to take the second derivative, right? So let's go back to our first derivatives. And maybe there's a way to write it so it's not quite as bad. I think since they both contain, e to the t, we can factor out e to the t, and then just write cosine t minus sine t here. Same idea here, we'll just write sine t plus cosine t. And then we can take the derivative from there, right, using product rule again. It's still not awesome, but it works, so we'll call this u and v. So the second derivative is going to be e to the t, the same basic thing, and then plus e to the t again times the derivative of the inside, which is going to be negative sine plus cosine. Same idea down here. We're going to take the derivative. It's going to be e to the t, this thing, plus the derivative of that piece is going to be, well, e to the t is going to be there too, but the derivative of sine is cosine minus sine, and that's the second derivative. You got to plug in pi over 2, so we're going to get e to the pi over 2. When you plug in pi over 2 to sine, you get 1 plus 0, so it's going to be 1 plus e to the pi over 2. You're going to get 0 minus 1, which is negative 1. So basically these are going to cancel out. So the second derivative with respect to y, sorry, the y coordinate is 0. For the x coordinate, when you plug in, so now we're plugging into this one. I'll do that down here. If you plug in pi over 2, you're going to get e to the pi over 2 times 0 minus 1 plus e to the pi over 2 times sine of pi over 2 is negative 1 plus 0, so it's that. So this is going to give us negative 2 e to the pi over 2, right? This is the second derivative of the x piece. And so the acceleration is the x piece is negative 2 e to the pi over 2, and the y piece is 0. So the y piece is not accelerating at pi over 2. All right, let's see. Okay, this next part, I don't know if they actually asked this on the AP exam or not, but I'll have to look it up and see if they do, but let's go ahead and do it anyway. There's the next piece that they're asking here is to find the tangent vector and the normal vector. Basically, like a vector is like this, right? So a tangent vector would be, something that's tangent to it like this, and the normal vector would be the one that, is going in the perpendicular direction to it. We can write a formula up here. The tangent vector at t is going to be given by r prime, which is the derivative of our vector value thumb function. Remember, we defined r as e to the t cosine t, so it's basically the derivative function that we already calculated, divided by the magnitude of the velocity. Oops. The magnitude of the velocity at t, which, if you remember from the last lesson, the magnitude of a vector is basically just the Pythagorean theorem thing, which in this case it's going to be like the speed, right? The magnitude is going to be the same thing as this speed right here. So you could think about this as speed, right? So to do this, so this is the tangent vector. It's basically going to be the derivative divided by the speed. So luckily we already calculated the r prime of t, right? Because we want this at pi over 2. So we know the r prime of t piece. So we know that t of pi over 2. The r prime piece is simply what we had down here, right? So it's going to be still, it's kind of weird to write this, but it's still here because there's two different pieces of it. And the denominator is simply the the speed, which is the square root of these things that we have on top added together and squared. So negative e to the pi over 2, e to the pi over 2, and then it just requires some simplification, right? So it's going to be the top we're not going to mess with right now, and the bottom we're going to go ahead and simplify it a little bit. Negative e to the pi over 2 squared is going to become positive, right? Anything squared is positive. You multiply that 2 in to get pi, like such. And then plus this one squared is also going to give us e to the pi. So basically together this is going to give us the square root of 2 e to the pi, which could be written as square root of 2, right, times the square root of e to the pi, which is the same thing as, square rooting is the same thing as raising to the 1/2 power. And then this exponent is going to multiply in there to give us e to the pi over 2 again, right? So this is going to give us, this is the numerator still, the square root of 2 times e to the pi over 2. And then once we're at this point, we can go ahead and just kind of break it into the two separate pieces, right? That's going to be the x piece, and that's going to be the y piece. So our tangent vector at pi over 2 is going to equal negative e to the pi over 2 over root 2 e to the pi over 2, comma, e to the pi over 2 divided by root 2 e to the pi over 2. And you can see that like this is going to cancel with that, this is going to cancel with that, and so we'll be left with negative 1 over root 2, comma, 1 over root 2, and that is going to be the tangent vector. All right. We can also talk about a normal vector. So you can see like it's pretty complex, but it's not undoable. The normal vector let's go back up to our notes section and write the normal vector. I know you don't have any space on your paper at all probably at this point, so maybe just a separate sheet of paper or something. Normal vector is going to be given by, we're going to call it n of t because it's the normal. Remember, that just means perpendicular vector. Is going to be t t prime of t. So like the tangent vector, I found the derivative of it over the magnitude of the tangent vector. So basically it's kind of like a second derivative in that you have to, like, the t was defined as a derivative and then you have to take the derivative again. Let's wait on this and maybe we can talk more about this later because it is a bit complex. And we'll throw some examples maybe with the tangent vector and then we'll see about the normal vector later.